Okay, before solving the example problem 34 on page 320, I want to say one more thing that I forgot earlier. It's very, I think it's very important, like why counterclockwise is the convention for positive. Okay, so if the rotation is counterclockwise, we're gonna say that's a positive direction, and the reason is really right here. Because again, when the rotation was counterclockwise, using right hand rule, we find out the thumb was pointing along the z direction. And how do we use right hand rule again? We put our four fingers, first of all, stretched out from the thumb. Thumb is perpendicular to the index finger. Okay, just open up your hand first, and then curl your four fingers along the rotation direction, which is counterclockwise. Kind of center the origin, okay, and then rotate around that with your four fingers. What you're seeing is the thumb is pointing out of the page, and that direction is, as shown on the left side as a perspective, that's the positive z direction. It is the positive direction though, okay? It's not the negative z direction. So if you do the similar thing with the, let me just change the color here. Let's do it for the counterclockwise case. Clockwise rotation. Okay, let's say that rotation is clockwise. Then what do you get? Again, now you're gonna turn your fingers that way, but what you see is you need to flip your thumb 180 degrees so that it faces towards the negative z direction, right, opposite to the positive z. And what you're seeing is it will be that direction, right, and that is negative z. So that is the reason clockwise is conventionally taken as negative, but counterclockwise is taken as a positive direction, and it's all about the cyclic order of the like the Cartesian coordinate system. You have to do it from x, y, z, and then you cannot really, like, this y and z could not be changed, okay? So you cannot switch those. It couldn't be x, z, and y. When you go in a counterclockwise order, from this to that to this, you have to follow x, y, z. That order is so important, and that's going to be very important later on when we talk about cross product between vectors, and that's coming very soon. So I'm going to go back to the example problem now, knowing that a disk initially at rest begins to rotate with a constant angular acceleration about an axis through its center. Okay, so the rotation is from right at the center, right? So it's right there. This is the rotation axis. And as you can see, the rotation is following the arrow given. It is counterclockwise, right? Remember, counterclockwise gives you out of the page direction for the angular velocity. Okay, so you're applying right hand rule. Now you're going to put your hand perpendicularly to the surface and curl your fingers, four fingers, along the arrow direction, counterclockwise direction. You're going to see that your thumb is coming out of the page, okay? And that's the positive direction. Okay, so what else do we know? After 10 seconds, the disk has rotated through 40 radians. It will determine the angular acceleration, the average angular acceleration, the instantaneous angular acceleration at 5 seconds, which is helpful what is given, and the additional angle that the disk will turn through in radians if the disk is allowed to turn for 10 additional seconds. Okay. On top of that 40 radians, we will find out how much more radians it's gonna take. Okay, so several things that we're investigating, but I really want you to take an advantage of the mapping, x to theta, v to omega, and a to alpha, and treat this as almost like a chapter 2 problem. Okay, yes, there are some other things like counterclockwise motion and stuff like that, but rotation and such that, but it's really similar to what we've done before, and we started in chapter 2 in the beginning of the semester. Okay, so this is nothing completely new. It's pretty much what we've done before. Okay, so what are the assumptions? First of all, is this a particle? Okay, it is not a particle, it's a rigid body rotation because any point on the object doesn't have the same velocity, right? Same direction and same magnitude. It doesn't have that. They don't have that. So it's a rigid body rotation, and but it is constant angular acceleration as it's said here. So it's very important. That means constant acceleration equations in angular form will be applicable. Okay, so we're going to think about that in the plan. Yes, so next is the plan, and we're going to say we'll use the rotational motion equations or constant angular acceleration motion equations. Okay, so you can name it as you wish. So the next thing is the estimate. Part A is angular acceleration of the disk. So when you find the acceleration, it's like, kind of think about this, it's alpha, but you can use what you know, especially since this is the first example. Try to make the analogy between linear and rotational. So you know that x equals to v0 xt plus 1/2 axt squared, right? What we know is initially this is at rest. So there's no velocity initially. So it's kind of x equals to 1/2 at squared. But instead of x, we have theta equals to 1/2 alpha t squared. And we are trying to solve for alpha. And we know that theta is 40 radians, t is 10 seconds, and that's going to be squared. There's 1/2 as well, but I think it's going to be less than 1 radians per second squared. But in order of magnitude, or in terms of like given just like 1 digits or so, you can say that the estimation is 1 radians per second squared, just like here. Okay, and that's for the angular acceleration. Next is angular velocity. So when I find angular velocity, I'm gonna use delta, like kind of think about like velocity equation. V is equal to what? Delta x over delta t, right? But instead of v and x, we have omega and theta, and we know that has 40 radians turn, and that's kind of my delta theta divided by the time interval. So it's going to be 40 divided by 10. And I'm going to get 4 radians per second. Okay. That's my estimation. And I think I already got the answer on this one. It was pretty easy that we could do it in mine. And next one is the instantaneous angular velocity, but not at 10 seconds. It's at 5 seconds, like kind of somewhere in the middle. Okay. And since this is a constant angular acceleration, and they're asking for the half time, you may think like you may not see that how they're exactly related, but because of the kind of the numbers given, and again, it's okay to say order of magnitude is like 10 radians per second, but I think it's going to be closer. Actually, it's going to be the same as 4 radians per second. Because of that 5 seconds, right? Half of that total time. Okay, because of that, it's going to be the same as part B. So it's not really 10 radians per second, but it is 4 radians per second. If they said that t is equal to 10 seconds, then I would say it's definitely more than 4 radians per second, because 4 was average, right? And later on, at 10 seconds, that's going to be the maximum, because it starts from 0 and is keep increasing, but 5 is in the middle, so that's why I'm saying it's going to be the same as average in this case, because the acceleration is constant. So we'll see. Again, just do your best on the estimations. You don't need to, if you don't see it right away, you don't need to go too much in details, but to be more specific, I think this is also 4 radians per second. And the additional angle that the disk will turn through in radians. Okay, so extra 10 seconds. First 10 seconds versus second 10 seconds. If you think about those motions, first 10 seconds, it rotated through 40 radians, starting from 0. Are they going to be the same? They're not going to be the same, right? Because you are starting with an initial velocity in the second motion for this additional 10 seconds. And you're going to reach to an even higher velocity at the end of that additional 10 seconds, that means you're going to cover even more than 4 radians in the second case. So if it was the same, then you would have 8 radians total, but it's not going to be more than that. So I think saying 100 radians is a good estimation, but it should be definitely more than 80 radians for sure. Okay, so it's very similar estimations. Again, also kind of practice the units as well. Acceleration is radians per second square instead of meters per second square, and velocity is radians per second, and the angle, additional angle, they're asking about angular position, that is in radians. Now we're ready to solve, and again we're gonna do similar thing. Okay, we're gonna apply our step-by-step solution. So first of all, we are writing our equations. This is our position equation, this is our velocity equations, and there are 2 of them only. Okay, we don't worry about any other equations. And what is at the start? Let's think about the step 2, kind of what is given at the start. We know that initially it was at rest, so omega 0, angular velocity, initial will be 0. Okay, and we can also define an initial theta to be 0, so that the 40 radians given it was the displacement from initial to after like the first 10 seconds. But if we set the first one to 0, then the 40 radians will be our final, and when we are writing at the end, we can put theta to be 40. What is the time in between? It's 10 seconds, right? Now we're gonna do our step 3, plug the numbers in and all these things in, combine them. So let's get rid of the things first. Omega 0 goes away, right? Theta 0 also goes away, and that's it. So the first equation becomes this: theta is 1/2 alpha t squared, and the second equation becomes that omega is alpha times t. Now plugging the numbers in, these were the, like from here, this is step 2 kind of. Put those in there, and you're gonna get alpha from here, and once you get alpha, you can solve for omega from there, and that's what we're doing. Again, this gives you the alpha, and alpha is 0.80 radians per second. Again, because of this equation, I thought it was going to be less than 1, and it is. But 1 radians per second square was a good estimation as well. It was close enough. And for this is part A answer. Let's box that. And the average angular velocity is delta theta over delta t. And so when you put these in, delta theta is 40 radians, delta t is 10 seconds, and I'm going to get 4 radians per second. Why can't I use this one? Be careful with that, okay? This is the omega at 10 seconds. That is instantaneous omega, okay? So if they were asking me to find the angular velocity at 10 seconds, that would be the instantaneous. Then I would use these two, right? Put this alpha in there, multiply by 10, and I would get 8 radians per second, per second for the omega. But they're not asking that. They're asking for the average. Average equation is what? Delta theta over delta t. Use that to get that, okay? And I'm going to continue the next in this next video.